Hi, this is Group 19. I'm Aaron, and I was in charge of arm design and gripper design.
Hi, I'm John, and I was in charge of color sensing and the ultrasonic transistors.
Hi, I'm Harry, and I was in charge of movement and navigating the arena, and we all worked together on the software side of things. As a group, we decided to go with a simple lifting mechanism. Two upright columns made out of 3D laser cut plastic, each had a servo on the end, which then connects to an arm made out of 2 bits of plastic. The arm then connects to the gripper. We did not put a servo on the arm because the weight of the gripper was enough to keep the gripper parallel with the ground at all times, which is what we required for our design. For the gripper, as no members of our team had ever done any 3D design work before, we thought it would be best to source a gripper online. We were able to find a simple gripper that used gears and one servo to open and close its cords. Although a simple design, we found a basic arm and claw very capable of picking up, holding, and placing down parts. Here's some footage of the arm and claw in action. The video also nicely shows how we're able to program the robot to remember the puck stack height and hence release the puck from the appropriate distance as more pucks were stacked. For puck detection and also color sensing of pucks in the arena, we designed a color sensing unit that attached to the top of the gripper. The color sensing unit comprised of an RGB LED that lit up different colors and also a photoresistor. We measured the value of the photoresistor when the different colors were lit and then decided what color was being sensed accordingly. The photoresistor would also be able to measure the absence of a puck. An ambient light reading was calibrated onto the robot at some time before. You can see the robot getting an ambient reading of the arena ground at the start of this video. The robot would then be able to go to a set position and keep moving forward until a puck was detected by quickly flashing through the color sensing algorithm and comparing it with the ambient light reading of the ground. For navigation of the arena, our robot relied heavily on the shaft encoder, which keep track of real revolutions and hence give a number representing distance travelled. However, the further the robot travels, the greater the error given by the shaft encoder becomes. We also found that due to slight inconsistencies in the arena surface and or slightly different motor speeds, we would often get quite bad veering to one side of the robot. To combat these issues, we reset shaft encoder numbers regularly, but also made our robot align itself on the wall by reversing into it until 2 mechanical switches on the back of the robot were pressed. An example of the robot aligning itself several times on the arena walls can be seen in this clip. To detect the block and also make sure our robot placed the pucks perfectly down in the designated area, we made use of the ultrasonic sensors. The ultrasonic sensors send out an ultrasonic wave and then count until the reflected ultrasonic wave is sensed. The count is then converted into a distance which we can use to make our robot accurately move around the arena. If we were to do this all again, I believe our robot would be much the same, however more refined. After seeing other groups' robots, there seemed to be 2 main lifting mechanisms that were used: an arm system like we implemented, and a lifting system. We like our robot's arm, however one thing that could be improved on our robot's arm is its reach. If our arm had slightly more reach, it might have been able to detect puck color without actually picking up the puck, and would also have been able to pick up pucks from the second column without affecting the first column of pucks. A smaller gripper core would also have been beneficial, as then we would be less likely to mess up the puck array, which makes picking up the subsequent pucks easier. Thank you for watching Group 19's team presentation video.